No, I think it's...
Always you just when it's not.
Ah, okay.
Nobody actually got it.
Okay, yes. Aha, but...
Do you? But then I will go down on the side then.
Yeah.
And just don't go there.
Yeah.
But
Okay,
just
yes,
go
yes.
there.
Yes, you're
And in
right.
fact, if you afterwards have the microphone,
Yeah.
Raz, step 3.
Yeah, it was. No, I live in the U.S. a number of years. Now I live in the UK.
Yeah, okay.
Yeah, no, not so long ago. In fact, I have lived in the UK for 7 years. Yeah, it was a big move.
So how do you like it? From somewhere in America to somewhere in the
Oh, no, I like it. I like it. I mean, Bath in particular, I always have been there. It's a beautiful city. No, it's a beautiful place. No, in general, I enjoy the UK. I like the weather. You know, because it's never too cold, never, at least that part of the country, you have some rain, but there is almost every day there is some sunshine. So it's not like,
No, that's like
Bath is southwest.
southwest, yes.
It's very close to Lisbon.
Okay. But it's not so much to the west as Devon.
Yeah, it's more to the east. It's almost in practice a suburb of Bristol. I mean, it's not exactly, but we are distant 15 kilometers, something like that. It's a nice place. I like it. I think it was also good for our kids. Yeah. Yeah, I understand. But there is, yeah, okay. If I do, would be rare. I'm not sure that I will make it. I really want it.
By the way,
Thank you very much.
it's time to start.
What time is it?
It works.
Hello.
Oh, it works, okay.
Okay, time is 9 a.m., so it's time to start this morning session. And it's a great pleasure for me to introduce the first speaker for today. It's Professor Manuel Del Pino. He's from Bath University in United Kingdom, and his history, well, very brief, is that he's originally from Chile, Santiago, and then he went to United States, to Minnesota, in Minneapolis, and I think it was there you took your PhD degree, is that correct?
Right.
Okay, yeah. But now we have the pleasure, at least from a European, Asian perspective, that you are now in Europe, so enriched our scientific culture here, okay? And you will talk about compact equilibria in the liquid drop model. So please, it will be very nice to have you here with the talk.
There's no... Yeah, now it works, okay. Okay, so thank you very much for the nice introduction, and and my very special thanks to the organizers for the invitation. So it's an honor for me to be in this great conference, and of course, first time in Kazakhstan. That's also a great opportunity for me. So thank you very much. Okay, so today I would like to speak about a problem in the calculus of variations, which is called the liquid drop model. I will be introducing what the variational problem is, not really the physics, because I'm not really an expert in that, and what is known and what have been our recent results on that. So all this is collaboration with Monica Musso from University of Bath, my home institution from with Andrés Zúñiga, a collaborator in Chile, in University of O'Higgins, and Rupert Frank, who many of you probably know from Germany. Okay, so what is the problem or the model? Okay, so this is an energy. So where the argument is a domain, a bounded domain, the pointer doesn't work, but well, you can see the energy is the sum of the perimeter of the domain, which means in the smooth case the area of the boundary. Okay. So if well defined, it coincides with the area of the boundary, and there is yet a second term, which is called the RC of omega, which corresponds to Coulombian interactions between points of the domain. Okay, it's an addition of these Coulombian interactions weighted. So, okay, assuming some form of uniform density. It is a repulsive kind of interaction. Okay. So, what do I mean by that? That if you want to minimize the energy, okay, say you want to reduce perimeter. However, the other guy, you don't really want to minimize, because if omega is very elongated, then you would expect that the second term becomes small, right? So it doesn't want to minimize, okay? But it reflects two different effects. The perimeter, the area of the boundary, is a surface tension effect that wants to keep the particles located inside omega, say, close to each other, while the Coulombian interaction wants to repel them. So, okay, so stationary state or critical point of it, where the argument, I insist, is the domain itself, say, is a form, is a shape that is not completely obvious. Okay, so this is actually a celebrated model in nuclear physics, introduced by Gamow in 1928, and then developed by many other people. And what this energy represents is the energy of a nucleus. And a nucleus is an object, or is idealized as an object consisting of nucleons, where the nucleons are protons and neutrons, okay? And the Coulombian part want these guys, the protons to repulse one to each other, while the perimeter term wants to hold them together. This is more or less a rough interpretation. So we assume that all these guys, all these particles, thinking that these guys are particles, are uniformly distributed in such a way that, say, if we think that the number of nucleons is a constant, okay, say it would therefore be assuming, you know, that there is uniform density in the distribution. The volume of omega will be proportional to the total number of nucleons. So it will assume that so far. So what is the natural variational problem with it? Since I am thinking about organizing in a certain optimal way these particles inside the region omega, then the natural constraint is the number of these nucleons, right? This is not supposed to be deformed, so the natural constraint is a constraint of volume, okay? The fact that the volume is equal to a certain constant that I will generically call m, okay? For mass, obviously. Okay, and what am I looking for? What I am interested in is about critical points. Critical points meaning domains that make the first variation of that energy not equal to zero, but equal to zero subject to perturbations of the domain that preserve the volume, okay? And that yields a relation that you can find simply by Lagrange multiplier rule and after some computation that I will show you next. Well, what is the basic example of one of these critical points? It's a minimizer. So maybe the most important variational problem associated with it is that of minimizing the energy E of omega under the constraint that the volume of omega is m. So what is it known about this problem? As I will try to justify to you intuitively at least, minimizers do exist for sufficiently small mass, while they do not exist for large mass. Okay, this is already well known for the problem, but that doesn't discard other interesting configurations that might appear. So here I explain again what do I mean by the stationary problem. That corresponds to finding a domain omega with vanishing first variation of the perimeter, not of the perimeter, of the energy. With respect to normal perturbations of the boundary, this would be a natural way to perturb the domain. Now, it turns out, and this requires some computation, quite a bit of computation, but mostly classical, okay? In the smooth case, this stationary condition amounts to solving what I'm calling there problem P. So problem P is just the mean curvature of omega plus the derivative of the Coulombian interaction, but measured only at points at the boundary. Okay, Bohr and Wheeler introduced this problem. So the energy was already introduced, but this Euler-Lagrange equation seems to appear first time in this work by Bohr and Wheeler. And their purpose was to compute the minimal energy required for nuclear fission. So it was a serious physical problem. Okay, let me quickly review what the derivation of this problem P from the functional, okay, using essentially a Lagrange multiplier. Okay, so what I will do will be to find an expression for the energy along variations or deformations of omega along the normal direction of the boundary, which is a natural way of parametrizing small deformations of it, right? Okay, let me give a name to this. Sigma h is simply a normal graph on a surface sigma, okay, and it's given by that expression. And omega h, by definition, will be the volume enclosed by sigma h. So critical points of the energy subject to volume constraint correspond to compute the first variation, namely a derivative of the energy evaluated at the omega deformed, where the parameter is the deformation, equal then lambda times derivative of the volume, right? So this is Lagrange multiplier's rule. Okay, let me quickly review why do you get the Coulombian term. So if you expand the Coulombian term, you see after, a formal Taylor expansion, you will see that the Coulombian of the deformed omega h is the Coulombian of omega plus that term there, integral of h multiplied by that factor. So this is just an easy derivation. And therefore, say we have the expression here for C of omega h. And if you expand the volume, what you see is that the linear term associated to the variation h is the mean value of h, exactly the mean value of h on the boundary. In addition, and this is a standard formula, also we can expand the perimeter, the area of the boundary. The area of sigma h, in other words, this rather than perimeter of sigma h should be the perimeter of omega h, of the volume enclosed. So it would be the perimeter of omega plus the integral over the boundary of the mean curvature. So the mean curvature times the variation. So the mean curvature corresponds to the first variation of the perimeter term. Therefore, at the constraint critical point, we have the relation that you can see there in the first line, which, if you collect the terms together and use that h is arbitrary, then you get the relation mean curvature plus the Coulombian term equal to a constant. Yeah? And maybe it is worthwhile to compare what's the meaning of this term with the same problem where the energy is simply replaced by perimeter. If we replace the energy by perimeter, then the corresponding relation for critical points, for constrained critical points, is the mean curvature equal to a lambda, to a constant. So that corresponds to the problem of finding surfaces with constant mean curvature, or soap bubbles, okay? It's certainly a classical problem, classical geometrical problem. Let me remind you something. If sigma is a constant mean curvature, which is at the same time bounded and embedded in, not just in R3, but actually in Rn, the problem, by the way, I don't know if I said it at the beginning, I'm always thinking about dimension 3, okay? And this is why I'm using Coulombian interaction. And the constant mean, say, surfaces that are bounded and embedded and that have constant mean curvature are necessarily balls, okay? This is the famous result by Alexandrov in the 1950s. Okay, so what do we have so far? So we have up there the energy, so the derivation of the critical condition, which is what I call problem P. And let me observe for you something. First, balls. Take omega to be a ball, okay? So balls have constant mean curvature for the boundary, right? But in addition, they make the second term also constant, because the second term is invariant under rotations. So if you evaluate at the boundary, you obtain everywhere the same value, right, at the boundary of a ball. And therefore, balls are critical points, if you wish, both for the mean curvature term and the Coulombian term. And therefore, they are critical for the whole thing. However, these two objects, as I mentioned before, have a very different character, okay? Balls are not just critical points of the perimeter term, but they are minimizers. So if you prescribe volume, the perimeter of the ball, or the area of the sphere, in other words, is the minimizer or among the perimeters of every region if you constrain the volume to this number m. And this is a well-known inequality that has a very long history in different versions, but with the language of modern calculus of variations, say where a good definition of perimeter is given, okay? The result is due to the Georgi in the late 50s. Rees, on the other hand, this is old stuff too, okay, classical. In 1930, proved that the balls are not minimizers of the Coulombian term, but maximizers, okay? Which is perhaps not too surprising. You want to maximize that guy there when you evaluate at points of the boundary, right? Sorry, the double integral up there, say you want the points as in average close, right? So that the denominator is big. So maybe it's kind of intuitive that this will happen if the domain is a ball. Okay. Okay. So the two terms in the energy describe opposite effects, and that makes the problem of finding critical points an interesting one. So in fact, this problem has a characteristic, as I will discuss in a moment, that the problem of surfaces with constant mean curvature does not have. And the characteristic is that this problem has compact and embedded solutions, okay, that are geometrically interesting. Now, to give you some intuition about the effect of small mass and big mass, let me play the following game. Let me scale, say, the volume of omega is m, okay? But let me scale it in the form m to power 1/3, so certain constant, which is the mass to the power 1/3, times E, where E is a new domain whose volume is 1, okay? So why do I do that? Because I want to see what happens with the scaling factor m to 1/3 when you apply it to the perimeter term and the Coulombian. And then you see that two different powers appear. In fact, in the Coulombian part, you see a power m to power 5/3 coming out, and from the perimeter, m to power 2/3. Therefore, you have the relation down there, which is that the mass to the power negative 2/3 times the energy, so certain constant times the energy of the original domain omega, is the perimeter of E plus m times the Coulombian of E. And what does that tell? That tells that, at least formally, the perimeter term will be dominant in that expression if the mass is small, while the Coulombian will be dominant otherwise. And that suggests, because the perimeter with volume constraint 1 has a solution, right? Has a unique solution, which is ball, right? If m is small, m times the Coulombian interaction, okay, will be a small perturbation. So it is to be believed that the existence of a minimizer for the perimeter will not be altered. And since balls are critical points, well, even more. Perhaps even the minimizer of that is a ball itself when m is small. Okay? While it also suggests that if m is large, the second guy is dominant, and therefore it is also plausible that there will be no minimizers. Okay. Now let me play the following game with the perimeter. If omega 1 and omega 2 are two bounded and disjoint domains, then the perimeter is, of course, additive in the way I show up there. And the Coulombian term doesn't add up directly, but you have it is the addition of the individual Coulombian terms plus a term of interactions, okay? So the problem, that term is more non-local, okay? Because it really involves, even if the two domains are far apart, there is a term in the energy, in the Coulombian term at least, that corresponds to those interactions. Then, imagine that omega 1 and omega 2 are sort of fixed domains, but located at a large distance one from each other. If that happens, then we believe that the interaction term will go to 0, at least formally, right? Now, let me consider the following number, the m star number. The m star number, that funny formula there, okay, which is approximately 3.51, is the number, the unique number that manages the identity that I am writing down there in the previous to last line, okay? What is the first term? The first term is simply the energy of a ball of of volume m star, okay? It's written in a funny way, but this is what it is. It's B1 ball of volume 1, okay? Of radius 1 perhaps, okay? And what that identity says is that the energy of a ball of volume m star is equal to this guy 2 times the energy of two balls with half the mass located at infinite distance. This is what formally that thing says. Actually, if you do the direct computation, this is nothing special. What you would see is that if the mass is bigger than m star, then the energy of the single ball of volume m will be strictly bigger than the energy of that configuration of two balls located at infinite distance. That energy will not really essentially alter if you put a tiny channel between them, for instance. So it doesn't matter if it is connected or not. What this says is that balls are no longer minimizers if the mass is big. Okay? So this is a big difference with the minimizers of perimeter, with isoperimetric inequality. Okay? When the mass is bigger than that number m star, balls are not minimizers. There is actually a conjecture, okay, in which some progress has been made over the years due to Choksi and Pelletier. Maybe it was stated by somebody else before, we don't know. But it is the following. If the mass is less than that number m star, then minimizers exist, and they should exactly be balls, okay? That's a conjecture, while it is also believed that if the mass is bigger than m star, the infimum is not attained. Let me tell you what has been, more or less what has been proven over the years. It has been proven that if the mass is sufficiently small, as we could have believed, balls are global minimizers, okay? So this is already established, and it was in fact established by 3 groups simultaneously in 2014, okay, by the authors that I'm mentioning there. While it is also very interesting that if the mass is less than m star, actually less than or equal to m star, minimizers exist, global minimizers. However, we don't know if they are balls, okay? So that part of the question is still open. On the other hand, Lu and Felix Soto proved in 2013, actually several years, quite a few years before, that no minimizer exists for large mass. Okay? There is no minimizer for large mass. And that result was essentially improved in a 3-page paper, very nice, by Frank Hillip and Nam in 2016, 3 years later of Otto, that if the mass is actually bigger than explicit number, 8, then minimizers don't exist. Okay, so this is the situation. There are, of course, many variations of this type of results involving changing, for instance, the perimeter into non-local versions of perimeter, like fractional, right? Or changing also the Coulombian potential by other Riesz potentials. So there are many works of that type, and I mentioned some substantial works in that line. Okay, so in summary, so just to complete the picture. Balls minimize up to a certain number m1. There exists a minimizer up to m star, so from 0 to m star. From m star and on, balls are not minimizers, and moreover, if m is bigger than 8, there is no minimizers at all. Let me mention one more result that is actually quite recent. It was recently published already in CPAM. It's a result by Chodos and a co-author, I believe his student. I'm sorry, at this moment I forget the name. They proved that actually M1, the number M1, can be taken 1. Okay, so below mass 1, the minimizers are balls. Okay, but there is yet another key number, 10. So what is 10? 10 is an interesting number because I told you balls are not global minimizers after m star. Okay, but you know it is reasonable, the picture, right? Because these two configurations of the two balls at infinity and a single ball seem to be very far away one from each other. The ball actually continues being a local minimizer. If you linearize, you can make the computation, say, of eigenvalues and so on, and prove that the thing continues to be stable up to a specific mass, 10, okay? Stable in the sense of second variation, subject to the usual constraint, right? I mean, under perturbations that do not change the mass. The ball is stable, so second variation is positive, up to 10. And from 10 and on, it's no longer stable. So something happens there. In fact, there is a bifurcation phenomenon coming from 10. This bifurcation phenomenon was discovered in old days already by Bohr and Wheeler in 1938. And looks more or less like this. I am taking this picture from a paper that by Xu and Du. It was posted in Archive in 2023. But actually, I just saw that it recently appeared. Okay? And it was recently published. This is a numerical paper in which they analyzed the bifurcation phenomenon, and they in fact found Very interesting stuff, numerically. So these pictures are taken from the paper of Xu and Du. Okay, so what they see is that there is a branch with two sides to the left. The horizontal coordinate is the mass, okay? This is what is called their chi. And the chi star, okay, is 10. Sorry, I simply adapted the picture. And what you see is to the left, you see things that are probably not minimizers, but actually mountain passes that take that form that called prolate, like an egg, okay? And to the right, instead, you see something that is presumably a minimizer, because in the bifurcation, the ball is not longer a local minimizer, so probably the one that goes down, the oblate, is a local minimizer. Okay, so this is the situation. It is interesting to mention anyway that Rupert Frank actually made this bifurcation analysis local, a la Crandall-Rabinowitz, say, very clearly, and actually he detected this phenomenon that I mentioned, mountain pass to the left and minimizer, local minimizer to the right. This picture is, well, it's not just imagination, but numerics, okay? Made under, I suppose, a class of axially symmetric domains by Xu and Du. And what they find is that, okay, the mass 10 corresponds to the number 1, okay? So you see 0.992, 1 point blah, blah, okay? There is the sphere, okay? And to the left, the branch will generate stuff like it is shown there. And look, at the even if you continue along the branch, you lose convexity, and you end up with a configuration that seems to be two balls connected by a small channel, okay? While to the right, with the oblate form, becomes a donut, you know, at the end, and presumably a torus, okay? For how long these things continue to be local minimizers, who knows? I don't think nobody knows that. Let me mention even one more thing, this is also contained in physics papers. The branch to the left, the one stemming from 1, okay? As you go to the left, you actually, at the beginning, you have a mountain pass, okay? Mountain pass meaning Morse index 1. But if you continue advancing to the left, at some point, you gain one more negative direction in the energy, and it's in fact formally not difficult to justify that the configuration of two balls connected with a small channel is not just a mountain pass, it's something with Morse index 2, okay? Okay, so that picture is mine. So well, it's just a reminder, you know, for what I've been telling you so far. You have the branch at 10, you know, and to the left you start generating stuff like that. And to the right, well, it's not so clear. And continuum balls are local minimizers from 10 to the left, are true minimizers from that number M0, which actually can be taken 1, according to Shodo's result, and so on. Okay. Actually, maybe connected with this shape seen to the right, I can mention a result by Ren and Wei on this problem, although they were motivated by some energy associated to polymers, okay? It was a different physical setting, but the same problem. And they discovered, in a paper in 2011, that if you choose a mass sufficiently large, then you can find an axially symmetric solution that looks exactly like a torus, okay? The problem that they had to solve was not truly a three-dimensional problem, because the problem is for the section, okay? And the section is something close to small circle at a certain distance from the vertical axis, and then that is rotated. And what you find is a certain type of weighted variational problem that they solve with perturbation methods. The solution is actually, and this is also believable, okay, it's unstable, however stable under natural axisymmetric perturbations. And by the way, there is a nice survey paper by Choksi Muratov Topaloglou, publishing notices in 2017. So you can see bibliography up to that year, although several things were done afterwards. By the way, the torus of Wei and Ren has the long radius, okay, is approximately m, the mass, times the log of the mass to power 2/3, while the small radius actually goes to 0, kind of slowly, as log m to power negative 2/3. If you compute the volume of the torus approximately, you will see that it is of order m, okay? Which is natural. What else can I tell you? Well, let me go back for a second to the world of constant mean curvature surfaces. This is, of course, in geometry, a very well-developed theory. There are many interesting examples, many constructions, also classifications for these objects. Definitely much less is known for the liquid drop model. Let me recall the simplest example, the simplest non-trivial example of constant mean curvature surface. It's a surface of revolution discovered by French mathematician Delaunay in middle 19th century. It's a family of surfaces that look like drawn there. So these are periodic surfaces of revolution with constant mean curvature that I will fix to be 2, okay? So the true parameter, once you fix the curvature, is the A. And what is the A? It's the neck size, okay? So those surfaces have a neck, okay, and the width of it, I call it A. And, well, it turns out that A actually goes from 0 to 1/2. At 1/2, you see a cylinder, the last thing to the right. The mean curvature of that is 2, okay? While if you start going to the left, you start seeing things like this wiggle shape. And then as the next size goes to 0, you end up with an array, okay, of an infinite array of spheres, one on top of each other, tangent, that are tangent one to each other. Yeah? These are the Delaunay surfaces. The regime actually from the singular array of spheres up to the cylinder, those surfaces are called unduloids. Okay? While you also see things that have self-intersections if you continue the parameter to the left, and these are objects that are not embedded. Okay? Okay, so here is another cute picture of a Delaunay surface. And actually, of one of the blocks. These guys are periodic, of course. Okay? They are periodic surfaces. And I am isolating one of the building blocks. So, the Delaunay surface is actually parameterized in polar coordinates by absolute value of x bar. Say x is x bar x3. Then the length of x bar is a function of x3. So the profile is a function of f3, positive function. Positive function that we can assume, of course, positive, okay? And also periodic. It is also periodic with a certain period that depends on the parameter A that I call TA. Okay, with this decomposition in mind, look, the surface sigma, the Delaunay surface, okay, can be written in that form as a union of the basic building block translated, okay, in k times the period, yeah, in the way I am suggesting up there. Now, let me consider yet another object, which is the truncated Delaunay. So consider the Delaunay surface with, or n blocks of it, and then we simply cut them. Yeah? This is what the sigma n means. And sigma nh is a normal perturbation of it, normal graph to it. Yeah? So this is notation that I needed for what I will explain next. Let me introduce even another object, the twisted Delaunay. Okay, imagine the Delaunay surface, okay, arranged vertically with a lot of these blocks, okay? And then pick the two ends and pull them together, okay? And that operation made in such a way that the axis, okay, becomes a circle, yeah? Becomes a circle with a big radius, okay? So this is what this twisted Delaunay is. If the radius is sufficiently big, we can parameterize the object simply using cylindrical coordinates, and the natural cylindrical coordinates for that are those that I am expressing there, okay? So x3 is sort of the arc length of the big circle. And capital R is the radius of it. Okay, so this is more or less and x3 is the perimeter that goes from 0, the length variable, the arc length variable of the circle that goes from 0 to 2 pi capital R. You need a relation, so R cannot be arbitrary, right? R is connected to n. And in fact, you need to have the relation 2 pi R, the perimeter of the circle, should be n times the perimeter. So I assume that. Okay. What is our result? We already received reports of the paper. The paper you can find in archive. It's not published yet. This is joined with Monica Musso, and Andrés Zúñiga. And what we found was the following. We found that there exist solutions like that. That there exist solutions similar to embedded solutions, similar to the twisted Delaunay, okay? It's not an obvious thing because you have the two effects, the Colombian and the other guy, and in fact, it is not so obvious what the effect of the perimeter of the incurvature compared with the Colombian interaction is. But we can handle them, and at least we can say that if n is large, I mean, essentially the result, the result says explicitly this. If you choose a sufficiently large mass, you can find a solution that looks like that for a certain number n sufficiently large, okay? And more precisely, it is the twisted Delaunay that I already introduced, omega tilde nh, the tilde is the twisting, okay? And the n is the number of blocks, and the h, the small normal perturbation. And that small normal perturbation is of order 1 over log n, okay? And of course, to have the mass equal to 1, you need to multiply by a number that is actually small, and it's of order 1 over log n to power 1/3 as well, okay? Okay, the main step to prove this is actually constructing a solution of the problem in which the number gamma in front of the Colombian term is actually adjusted, okay? This is a sort of Fredholm alternative type problem. It's a nonlinear Fredholm alternative. So what we need to find is a small perturbation of this basic twisted Delaunay. What we are able to find is an H, a normal perturbation of size 1 over log n, yeah? And a number gamma, which is also of size 1 over log n, so that this identity down here holds. Of course, you can absorb the gamma back to make it 1, okay? And that modifies the volume of omega and h, but essentially, you can capture not all big numbers, not all big masses, with that operation, with the volume of omega n h times gamma to power 1/3. However, a certain continuity argument will lead you to the fact that if you move A a little bit, then you can actually cover the entire real line for big numbers. Sorry, I went too far. However, this cannot be done without a condition. And the condition is that that integral, a certain integral quantity that we call I sub A needs to be positive. Let me tell you what that quantity is. It is that ugly integral up there, okay? That integral is an integral depending on the profile, and what you need is a sign for it. So you need that it is positive. And why it is necessary? Because that sign condition is what makes us possible to adapt the number gamma, okay? Okay, let me be a little bit more explicit. Then I have an error of approximation when I substitute the twisted Delaunay sigma n without the h, the twisted Delaunay sigma n tilde. If I replace it not in the energy, but in the object that you want, the derivative that you want it to be constant, then you get that number there, E gamma of x given by constant the mean curvature plus gamma times the Coulombian term, yeah? Okay, what we would like is to estimate both mean curvature and Coulombian term for the Delaunay surface and for a small normal perturbation of it. So, you may wonder where this log n comes from, okay? It's not difficult to explain. It's because of this. If you compute the Coulombian term in omega n tilde, in the twisted Delaunay, then you will see that at main order, you find a sum of those integrals. Those integrals are all of size, omega 0 is the basic cell, of size 1 over k. So the total Coulombian interaction is going to be the volume of the basic cell plus a sum of 1 over k, right? And that sum of 1 over k is what gives us the log n, yeah? So this is why the log n comes into play. And this is in fact crucial, very, very important, that number is big. In fact, if you expand the mean curvature of the twisted Delaunay, you find 2, as it is obvious, but corrected a little bit because of the curvature of the circle. And that corresponds to that certain function of x3, explicit and positive, multiplied by sine theta, where theta is the polar angle of the small section. Okay? Then, after some computation, then, what we get more precisely is that the error is 2 times, you get a constant, yeah, at main order, 2 minus gamma times VA over T log n, okay, this is a big number, plus another object, and plus this term of error down here. So, what is the problem? The right-hand side is not a constant. It's a constant at main order, if you wish. But in order to eliminate the last term in the error, and also the previous two last in reality, but mostly the last one, you need a certain solvability condition, a certain special choice of gamma. This is not for free. So this is why we need to introduce a small perturbation of sigma n that I call sigma nh, and I need to use these formulas up there. This is an expansion of the mean curvature of the twisted Delaunay perturbed that actually gives us the same object but without twisting, and plus the terms that you see there. One is 1 over n times sine theta, and then terms that go faster to 0 with n. The mean curvature of sigma nh you can also expand in this form here, and this is where the Jacobi operator arises, the Jacobi operator of sigma n in the expansion. The Jacobi operator is the linearization of the mean curvature, and is defined like this. The good thing about the Delaunay is that we actually know that it is not degenerate in the sense that the Jacobi operator can be inverted under correct topologies. Okay? Well, for the expansion of the Coulombian operator, you also have the explicit expressions. In total, the full equation for the perturbation H can be written as you can see there. The Jacobi operator at H equal to this expression of the error that I showed you, plus this other ugly guy times the integral of H, and plus some small terms, okay, that I call L1, and this guy here is quadratic. So small terms and a constant. So this is the problem that I want to solve. So this is kind of, telling us that I should choose integral of H equal to 0, otherwise that term comparatively wouldn't be very small. Luckily, and not luckily, actually it is natural that the perturbations that they have to take have mean value 0 so that the volume is conserved. So I assume the integral of H is 0. And then the problem that I need to solve involves those functions up there that appear in the expansion of the error, and the perturbations have to be taken with mean value 0. And then I have the expression up there, which is nothing but Fredholm alternative for the Jacobi operator. So if you want to solve inhomogeneous problem for the Jacobi equations, if you want to invert the Jacobi operator, you can do it, provided that certain solvability conditions or orthogonality conditions are satisfied for the right-hand side. In particular, you can find a function that is explicit. You don't even need Fredholm alternative to that, just explicit formula. You can solve Jacobi operator of a certain test function phi equal to 1. After doing that, the problem that is really relevant for me is Jacobi operator equal to the right-hand side plus c times nu2. So I cannot avoid that because that's part of the kernel that I cannot get rid of, plus a d, which is a constant. And the numbers c and d can compute it in this way, pretty much by definition. So it turns out that that problem is solvable. I can find an h which is a linear function of g such that this happens. That's essentially Fredholm alternative in which I need to make a good testing using that function bar phi. Okay, and this is the linear result needed. And what is the last thing? Well, we solve the nonlinear problem simply by perturbations, by a fixed point scheme based on that inverse. Yeah. Finally, what I need to do is to solve then Jacobi operator at H equal to certain nonlinearity, okay, that I call E, not a good name, but doesn't matter. Okay, it's a function of H and gamma that can be written as the fixed point problem, they are in blue, and I solve for H, the first problem, which I can do it because T applied to the thing is a contraction mapping for small h. And then I solve it as a function of gamma, the h. I substitute in the second equation. And the second equation, if I expand what it means, it tells me the condition that I need. Let me be more specific. That relation that I write up there is the relation that you need to be satisfied. You want that 0 is equal to an expression that at main order looks like that ugly integral IA multiplied by a constant minus C2 gamma times log n and plus smaller order term. And that tells me that at main order, the sum of the first two guys should be 0, okay? And this is how we find gamma. In reality, gamma can be solved that way, say in exact form, yeah, where the IA enters into play. Now, the IA is positive for small a. This is something we can prove directly. It is also positive if a is bigger than 1/4 and less than 1/2. And in between, we strongly suspect it is positive too, but and numerically you see that, but we don't have explicit proof for it yet. Okay, but doesn't matter, at least for small necks, for instance, we have it. Okay, so as a conclusion, we have the existence of things like this, and what I sketch here is simply the continuity argument needed to cover all large masses. Let me finish with one thing. Is what I mentioned you before about the behavior of the branch, yeah, as you go to left, okay, with small mass, okay. This is what the picture of Xuandu says. You will start seeing stuff like that, yeah. Solutions that mountain pass or higher Morse index solutions that are made up of two balls connected by a neck. So their pictures then suggest that the left branch coming from m equal 10 give rise to these two balls joined by a tiny neck. This configuration is certainly not a local minimizer, and as I told you, it is formally something with Morse index 2. Okay, this is joint work with Rupert Frank and Monica Musso, and we managed to prove that those solutions exist. So we can find solutions with small mass made up by two balls connected by a tiny neck. What is the tiny neck, by the way? The tiny neck has a different scale. Yeah, it's much smaller, right, than the rest of the things. And that tiny neck actually has a shape that is approximately catenoidal. It's approximately a catenoid, okay? So the basic rotationally symmetric minimal surface, and then you put on top of that a ball and down another ball. And this is a good answer to construct a solution with methods of perturbation gluing methods similar to the one we used before, except that the difference in this problem is that we need to consider the two different scales, okay? The geometry is simpler, but the fixed point argument is, if you wish, a little bit more sophisticated. Nothing so special. It goes along the same lines, okay? So I will simply skip this. But of course, what we need to do is to construct a good approximation to the solution to begin with, and then devising an argument that allows us to prove the existence of a true solution. And the way we perform that is by, again, by a solvability condition that will actually involve what happens not really on the neck, but on the sphere. Yeah, well, anyway, so these are the computations necessary to go through that. This is the ansatz for the final perturbation, a perturbation associated to the neck, plus a perturbation associated to the upper ball, and the other associated to the lower ball, and multiplied by suitable cutoffs. Okay? So the bottom line is to find a system that connects H0, H plus, and H minus. Yeah? And we solve the problem. We solve that system after adjusting a parameter that makes the problem sort of make the interactions weaker. Yeah, that's the bottom line. So the core of the procedure. So at the end, you have to solve a system for H plus and H0. Yeah, that deals with the solvability condition integral of the error in the upper part times the second component of the normal, which is a Jacobi field, equal to 0. And that yields the relation between the neck size of the catenoid and the mass. In fact, it is m times smaller. Okay.
Excuse me.
Yeah,
very nice talk so far, but there should also be some time for questions. So can you?
Yeah. Okay. Well, thank you very much for your attention.
Okay. Thank you very much for this very nice talk. So you were more or less finished when I came. Okay, that's very. Are there any questions or remarks for Professor Pino? Yes.
Well, thank you for your nice talk.
Thank you.
My question is regarding to that M star case of the mass of the ball. Do you have any idea on the sharpness of that M star? You know it's smaller than 8, if I got it.
Well, there is already certain clear evidence that of the role of the number M star. In fact, well, there is the conjecture that for all mass less than M star, minimizers are balls, okay? While for m bigger than M stars, minimizers simply should not exist. That's the conjecture. What has been proven is that if the mass is less than M star, minimizers exist. But it is not known that they are balls. While it is not known yet that balls are not minimizers do not exist for m bigger than M star, but it is conjecture. It is proven only for large m, for large mass, say. Very large first by Lu and Otto, and then by Frank for m bigger than 8. I mean, Frank and collaborators. That's what it is now.
Sorry. Then if I can make another question, I really hate these devices. How does the curvature of the domains affect that result?
Well, they actually play an essential role. For our constructions, curvature plays an absolutely essential role. So you couldn't, in fact, maybe it is a little subject technique. It is kind of subtle, but this number log n that I introduced before, for instance, has to be a large number appearing in this computation. If that number was capital O of 1, you could do nothing. And this is what happens in the case that you wanted a similar construction of constant mean curvature surfaces in simply constant mean curvature surfaces. Objects like that simply do not exist, okay? Because the only constant mean curvature surfaces are balls. Say, constant mean curvature surfaces embedded, I mean. So in our constructions, the presence of curvature is completely essential. It is also the case in the problem with the two balls, although in there it is not the curvature the main thing, but more the effect of the Coulombian interaction. Because the Coulombian interaction plays like this, okay? If you pull them out, one from each other, the energy tends to go up, okay? And so that's when negative energy defines a negative energy for the direction. So it goes down. And that's the extra direction if you wish. You can also modify the volume of one a little bit, of one of the spheres, up and down the other. And that remains the volume the same, but that also modifies the energy, okay? Because it modifies the perimeter part. So these are the two negative directions, if you wish, the Morse index 2 that I mentioned. So, no, a curvature, or more, the interaction of the curvature and the Coulombian is delicate and is what leads to the existence of these guys. Thank you.
So thank you very much for this question and reply. I think it's time now for the next speaker. So I'm sorry, we have to, there are for sure more interesting questions and so on, but I think we have to push this to the coffee break, okay? So let's thank the speaker very much again for this very nice talk, okay? We resume as soon as possible. Oh, no, My glasses are. So we just wait for the slide. Okay, it's time for the next talk in this morning session, and it's a great pleasure for me to introduce the next speaker. It's Professor Xiangjing Zhu from Chinese Academy of Science, and Professor Zhu is going to talk about some recent progress in several complex analyses. This sounds, of course, also very interesting. So, please, Professor Zhu.
Okay. Okay, can you hear me? First of all, I'd like to thank the organizers for inviting me to participate in the Congress. Yeah, it's my pleasure to be here. Today, I'd like to talk about some recent progress on several complex variables. Yeah, as you know, purely subharmonic functions are very fundamental in mathematics, which was introduced by Orca and Lalonde in 1940s. These functions means that this is an upper semi-continuous function. May take minus infinity, and is subharmonic when restricting on each complex line as a function of one complex variable. So singularity of a purely subharmonic function will mean the set of minus infinity of the function. A typical example is given by C log f1 modulo square plus fk modulo square. So here f1, fk are holomorphic functions. Complex analytic subset locally is the singularity set of purely subharmonic function. So very special case, you know, in calorimetric, calorgeometric, yeah. So you know, caliform locally having a potential which is smooth and strictly purely subharmonic function. So in particular, Bergman kernel. Yeah. So here we consider maybe a not smooth function and may take minus infinity. So with this concept, we can define a singular Hermitian metric on every holomorphic line bundle. So this geometric can be locally written as e to power minus phi. So phi maybe not smooth, yeah, just locally integrable. So in this way, we can still define the curvature current by dd bar phi. So in this way, we can define pseudo-effective light bundle. So this means the curvature current is positive. That is to say, phi is just a purely subharmonic function. So you can define a stronger concept, a bigger light bundle. So this means the curvature current has a positive lower bundle. And the more particular, you get a positive light bundle. So in this case, phi is smooth and strictly purely subharmonic function. So we have the concepts between various positivity on holomorphic light bundles. So you know this relation. Yeah, and here there are very important results by Kobayashi. So one is the vanishing theorem. If the light bundle is positive, you can get the vanishing theorem. So here, Kx means the canonical light bundle. Using his vanishing theorem, Kodaira got the embedding theorem. So if a complex manifold having a positive light bundle, so you can embed this manifold into complex projective spaces. Yeah. On the other hand, when you deal with the complex Mongian pair, you can also consider a singular or omega purely subharmonic function. Yeah, for any Hermitian manifold, you can define omega purely subharmonic function. Yeah, in this way, the function may be not smooth and may take minus infinity. So, for example, when, as you know, the definition domains of Mabuchi functional, Dim functional, K energy, and so on, consists of smooth omega purely functions. So when you but such definition domains in general is not complete. So when you do completion, so you get singular omega purely subharmonic function, which is not necessarily smooth. So of course you can define the equivalence between the singularities. So given two purely subharmonic functions, phi and psi. So phi is more singular than psi. This means phi is not bigger than psi up to a bounded function. So in this way, you can get equivalence relation. So for such equivalence, we have several important classical invariants. So for example, the typical example is the so-called Lalong number. So a purely subharmonic function, the Lalong number of a purely subharmonic function at one point is given by this limit of the function phi z over log absolute value of z minus x. So you can also define higher level numbers. So using complex Mongian pair operator. So in this case, one's level number is just the usual level number. Another invariant is given by complex singularity exponent. So this is the supreme of such past non-negative real set. Such that the exponential to minus 2c phi is locally integrable. Recently, we gave a relation between the higher level numbers. So we introduce a concept, the so-called LTT, log truncated threshold. So this is given by the infimum of the function capital F. So this is defined by some upper limit, which of the function phi z over log absolute value of z. So if LTT is finite, we get the following. So this we get inequality, the nth level number. So this is actually a complex Mongian pair mass. It can be controlled by the former J's level numbers. So in particular, so if the level number is 0, we can get the complex Mongian pair mass is 0. So in this way, we can answer the so-called the zero mass conjecture. So this conjecture says that if V1 is 0, then Vn is also 0. Another important invariant is the so-called multiplier ideal sheaf to a Fourier subharmonic function. One is associated to a multiplier ideal sheaf of the structure sheaf, so which consists of gems of holomorphic functions, such that this function is locally integrable. So you can also define the multiplier ideal sheaf associated to pseudo-effective Lie bundle. There are some important basic properties of multiplier ideal sheaves. The Lado proves that this multiplier ideal sheaf is coherent. Yeah, you know, in several complex variables, coherent analytical sheaves play a very important role in several complex variables and complex geometry. So this multiplier ideal sheaf is coherent, has a quick sequence of very famous result due to Bombelli, which says that local integrable point set of E minus phi is an analytic subset. So actually, this point set is just the zero set of the multiple ideal sheaf. The zero set is the support of the quotient sheaf or modular multiple ideal sheaf. Yeah, since multiple ideal sheaf is coherent, this quotient sheaf is also coherent. And the support of any coherent sheaf must be an analytic subset. So in this way, you can give one sentence proof of the famous result. So another property is the following. So multiple ideal sheaf is integrally closed. Yeah, so this means the integral closure of multiple ideal sheaf is itself. And another important property is the Liddell vanishing theorem. So if we consider a big line bundle on a weakly pseudo-convex Kähler manifold, so weakly pseudo-convex manifold means that there exists a purely subharmonic exhaustion function. So the conclusion is that the vanishing valued in canonical bundle Kx tensor the line bundle and tensor the multiple ideal sheaf, the cohomology vanishing for any Q bigger than 1. So in particular, when phi is smooth, of course, this multiple ideal sheaf is trivial. So this reduces to Kodaira vanishing theorem. And this vanishing theorem also implies Kawamata-Fiweg vanishing theorem, which is an important theorem in algebraic geometry. Joined with my former student, Min, we can drop the Kähler condition in Liddell's vanishing theorem. So this means we can consider a bigger holomorphic line bundle, and the manifold is a Hermitian holomorphic convex manifold, maybe not Kähler. We can still get the vanishing theorem. So on the other hand, Liddell's vanishing theorem can be used to give a unified solution to Levy problem in several complex variables, and Kodaira embedding theorem in algebraic geometry. So Levy problem is a very famous problem in several complex variables, which was solved by Orca for pseudo-convex domain in Cn. Yeah. So this means pseudo-convex domain is a domain of holomorphic. And for the case Levy problem on complex manifolds, this was solved by Hans Grout. He proved that Kähler exhaustion implies steightness. So Kähler exhaustion means the existence of a Kähler metric with global exhaustion potential. Demailly posed a conjecture about a very important property for multiple ideal sheaf, so the so-called Strunk-Opnis property. So we can consider the so-called asymptotic multiple ideal sheaf, which is given by the union of the the family of multiply ideal sheaves with a coefficient p bigger than 1. So by the Lottering property of the coherent sheaves, so this yielding can be stopped at one point. So we have some positive number epsilon naught such that the yielding is also a multiply ideal sheaf. So the Maillet posed the following conjecture. So for any purely subharmonic function, a symptotic multiply ideal sheaf is just the multiply ideal sheaf. So the conjecture has the following two equivalent reformulation. So the first one is as follows. So if the function f modulus square times e minus phi is locally integrable, then there exists some positive number epsilon naught such that modular f square times e minus 1 plus epsilon naught phi is still locally integrable. So in general, you know that the later function is more singular, but the conjecture says that this function, this more singular function is still locally integrable. And another equivalent statement is as follows. So the real number set such that f modulus square times e to power minus p phi is locally integrable. So this set is open. Yeah, it's open. So this is an open interval. So actually, this conjecture has a basic origin from calculus. Yeah, from calculus. Yeah, in calculus, you know, if the function absolute value of x to some power is locally integrable, then you can get some more singular function is still locally integrable. When the multiple ideal sheaf is trivial, this means e minus phi is locally integrable. So this case called openness conjecture was proved by Bob Benson. For the two-dimensional case, this conjecture was proved by Farley, Johnson, Mustard. So, joined with my former student Guan, we proved that the Maillet's strong openness conjecture is true. Yeah. So, in the same paper, we also state the following two forms using the same proof. Yeah, we can prove two forms. So one is if a sequence of purely subharmonic functions increasingly converges to a purely subharmonic function phi, we have still this equality. And another form is for two purely subharmonic functions phi psi, we can also get this equality. So this proof, this result was published in 10 years ago. And the proof of the Strong-Obnis conjecture is actually based on our research on optimal L2 extension theorem. So in a series of papers, and we also found the geometric meaning of optimal L2 extension theorem. So this geometric meaning was used in the study of Itaka conjecture and singular positivity of higher direct images, and BDPP's unirelease criteria for general Keller manifolds. So now let me mention some consequences of the Strong-Obnis of multiplier ideal shifts. So we can consider a section of the multiplier ideal, and a sequence of Purely subharmonic functions phi j increasingly convergence to phi. Then we can get the convergence in L1 locally. So the argument is as follows. So by the Strong-Obnis, we can get some J load such that the multiplier ideal shift associated to phi J load is just the multiplier ideal shift associated to phi. So after shrinking the domain, so in particular we can get the integral of f absolute square times e minus phi j law is finite. So since the function f modulo square times e minus phi j is dominated by this integrable function. So you get the corollary by the Lebesgue's dominated convergence theorem. And another corollary is as follows. We can also get the following vanishing theorem. So here we consider a more general pseudo-effective Lie bundle. And ND means the numerical dimension of the pseudo-effective Lie bundle. So we can get the vanishing theorem valued in the canonical bundle Kx times the Lie bundle and times tensor the multiplier ideal shift for Q bigger than n minus ND. So when the bundle is big, as in Nadel's vanishing theorem, ND must be n. Yeah, ND is equal to n. So in this case, you get Ladle's vanishing theorem. Another corollary is for a big light bundle, we have the following equality. The so-called asymptotic multiple ideal associated to a linear system, ML. And this was conjectured by Desmarais, Lawrence An, and Nazarbayev, which is also listed as an open problem in Nazarbayev's book. And here, H mean is given in Desmarais' theorem. If L is pseudo-effective, then there exists a unique singular Hermitian metric with minimum singularities. Recently, strong openness is also used to give some new approaches to Yao-Tian-Donaldson conjecture. So this conjecture says that on Faro manifold, existence of Ke is equivalent to K stability. For example, in the paper by Berman, Buxton, and Johnson, evaluation approach to the Yao-Tian-Donaldson conjecture. And in another recent paper by Davas Zhang, which was published last year in SIMPA journal. So in this paper, Davas Zhang discuss a general setting. So X is a compact Kähler, but the anti-canonical bundle is big, not necessarily positive. Yeah. So this is more general than being Faro manifold. So as a starting point is to introduce lambda dim functional. So the existence of positive lambda is guaranteed by the strong openness. And joined with my former students, Guan and Li, we got the stability of the multiple ideal sheaves. So this means we can let the multipliers F changed. So we consider a sequence of multipliers Fj. Yeah, this means the multiplier is not fixed. So we can still get the convergence in the local L1 norm. Now let's recall some basic classical theorems for solving D-bar equation with L2 estimate. So this is given by Hermander. Hermander proved the following theorem. So if D is a bounded pseudo-convex domain, so as I said before, so this means there exists a priori subharmonic function which is exhaustion on D. And the phi is a priori subharmonic function. So one can solve D-bar equation with the L2 estimate. So here C is some positive constant. So Homander's theorem is for light bundle. So his theorem was extended to vector bundle case. So now let me mention some basic notions. So now we consider a Hermitian holomorphic vector bundle on a Hermitian manifold X. So we have a very natural chain connection. So D is given by D bar plus D pan plus D bar. Yeah. So you can consider the chain curvature, and the chain curvature can be locally written as this form. So E1 ER is a local orthonormal frame, and Z1 Zn is a local coordinate. So to this chain curvature, we have a natural Hermitian form on tangent bundle tensor, the vector bundle. So you can get the Nazarbayev the Hermitian form. So for this form, we can define some positive properties. So E is said to be Lacaro positive. So if this form is positive definite as a Hermitian form on tangent bundle tensor E, so this means we for any U E-valued tangent bundle section. So we get this positivity. And you can also define glyphs positive. So this means for any point x in the manifold X, all can see tangent vectors at X, and S is a stock of the bundle at X. So we have this positivity. So you can also define negative by replacing positive with negative. Desmaillet proved L2 existence theorem for holomorphic vector bundles. So here, if the curvature operate B, this is a commutator of the chain curvature operate and gamma omega, which is adjoint of L omega. If this curvature operator is semi-positive on E-valued NQ differential forms, then we can solve the D-bar equation with this L2 estimate. So in particular, if you consider the vector bundle as a light bundle, so you can get Homander's L2 existence theorem. And recently, we initiated to studying the converse of L2 existence theorem and L2 extension theorem. So we get a series of papers. And then Hosono Ilayama also got some important results. So now let's state one result, which is a converse of Osawa-Takigosi's L2 existence theorem. So this function phi, we assume it is an upper semi-continuous. And if for any point with phi is not minus infinity at this point, and for any positive m, there exists holomorphic function such that the function at the point is 1, and the integral, the L2 integral with respect to e to the power minus m phi can be controlled by some constant times e minus m phi 0. Then we get phi is purely subharmonic. As you know, if phi is purely subharmonic, then we can get the L2 extension from one point. So this is the so-called Osawa-Takigosi's L2 extension. So we got the converse part. And we can also get the converse part for vector bundle case. Yeah, for vector bundle, yeah, if the vector bundle satisfies some L2 extension property, we can get this bundle must be Griffith's semi-positive. As for the converse of L2 existence theorem, we introduce a concept L2 optimal. So this means for vector bundle, if we can solve D-bar equation for E-volume NQ forms with L2 estimate locally, so we say this holomorphic vector bundle is L2 optimal. So by Hellman-Desmailly's L2 existence theorem, we have if the metric is Lacaro semi-positive, then EH is L2 optimal. Yeah, so this is the so-called Hellman-Desmailly L2 existence theorem. So we prove that the converse of the L2 existence theorem is also true. So we can get this if and only if. So EH is L2 optimal if and only if this metric is Lacaro semi-positive. So as an application, we can get a solution of Lampert's problem. So, for example, you may find this in this archive paper. So Lampert's posed the following problem. So he asks whether a smooth Hermitian metric, which is convergent by an increasing sequence metrics of Lacalo semi-positive. The limit metric H is still or not Lacalo semi-positive. So this is his problem. So the argument can be outlined as follows. So by Homanda de Mailly's L2 existence theorem, so since Hj is Lacalo semi-positive, then Hj is L2 optimal. Yeah, but in general, it's not easy to see Lacalo semi-positive Hj. The limit is still Lacalo semi-positive by the definition. Yeah, because the curvature involves the derivatives. Yeah, derivatives. So in general, we cannot get the limit is still Lacalo semi-positive by the definition. But the property being L2 optimal is preserved by the limit process. Yeah, so this, but yeah, you can see that, yeah, if for Hj we can solve, we have this, we can solve the bar equation, and with this L2 estimate. So here H, yes, so here is for Hj. So this property, you can prove that you can when you're taking the limit. So the limit for limit metric. So this is still true. Yeah. So this is still true. So this means the limit metric is still L2 optimal. Yeah. So being L2 optimal is preserved under the limit process. So and then using our characterization theorem, H is Lacalo semi-positive. So in this way, we can answer Lampert's problem. And now we already mentioned the results on Lie bundle, on Lie bundles, pseudo-effective Lie bundle, and also vector bundles. For vector bundles, we can define multiple submodules, subshifts. So it's natural to ask the Lie bundle, some results for Lie bundle, for singular Lie bundles can be extended to singular vector bundles. So you can define a singular Finsler metric on a homomorphic vector bundle. And you can also define a singular Hermitian metric on the homomorphic vector bundle. So the metric may be not smooth, just measurable, non-negative. So you can define the glyphs positive using this well-known result. So this result is for smooth Hermitian metric. So H is smooth, glyphs semi-negative. this is equivalent to say the H norm of the any local section is purely subharmonic. So using this equivalence, you can define singular glyphs semi-lective. So so if H is a singular Hermitian metric, and the H norm of the any local holomorphic section is purely subharmonic. And using our characterization of Lacalo semi-positivity, we can also define the Lacalo semi-positive for singular metric. So this means H is singular glyphs semi-positive, and H is L2 optimal. So you can define a multiple submodule sheaf. So this consists of the gems such that the H norm of this gem is integrable locally. So Hosono Ilayama proved that the multiple submodule sheaf is coherent, associated to a singular Lacalo semi-positive Hermitian metric. Joined with my former student Liu and Yang, we proved that this sheaf actually satisfies strong openness and stability, as in light bundle case. So this the meaning of strong openness and stability. So now let me mention some generalization of Le Bourdieu isomorphism theorem and Kobayashi-Ochiai isomorphism. So for a vector bundle, we can consider projective with the light bundle and the tautological light bundle. So Kobayashi-Ochiai get the following equivalence. So SM is the symmetrical power of the vector bundle. So left side is valued in vector bundle, the cohomology valued, but right hand side is light bundle cohomology. And also Le Bourdieu got the following isomorphism. Yeah, left side is a vector bundle valued cohomology, and the right hand side is light bundle valued cohomology. So we introduce a lecture positivity for singular Hermitian metric. So in this way, yeah, if this bundle has this positivity, then we can get Le Bourdieu isomorphism theorem and also Kobayashi-Ochiai isomorphism theorem. So in this way, we can generalize both of Le Bourdieu isomorphism and Kobayashi-Ochiai isomorphism, and actually we can recover their isomorphism theorems. And based on this generalized isomorphism, we can extend some results for light bundle cases to vector bundle cases. So for example, with my former student Zhu, we get injective theorem for pseudo-effective light bundle. So in this way, we can get the vector bundle case. And also, I just mentioned the vanishing theorem for pseudo-effective light bundle. And we can extend this light bundle vanishing theorem to vector bundle vanishing theorem. And also some homomorphic Morse inequality for singular light bundle case. We can get analog singular homomorphic Morse inequalities for vector bundle case. And also Davas-Scha's asymptotic formula for light bundle case, we can get a similar result on vector bundle case. Yeah. I think I stop here. Thank you.
Okay, thank you very much for this very nice and interesting and inspiring talk, and also for this very strong result. Are there any questions or remarks for Professor Zhu? Yes.
When you talked about the general Kawamata-Vivek-Nadel type vanishing theorem, you mentioned that the proof is done by combining Zhou's result with your openness. Can you recall what actually Zhou's result was? Or do you mean that conjecture you mentioned was actually proven? Well, it was some recent results, really a little bit earlier, but that theorem, yes. Well, okay, then I can ask you later about that. The other question I had was actually, you had a special result where you simply said, in a special case, that singular Griffiths positivity and your L2 optimality implies singular Nakano positivity. Is there a possibility to have that one in a more general case? I mean, there are these links between Nagano and Griffiths positivity. So could you get that Griffiths positivity plus your L2 implies Nagano positivity?
Yeah, this is a good question. Yeah. So up to now we solved the converse of Herman de Mailly's two existence theorem just for smooth matrix. Yeah, of course there should be a singular version. Yeah, but up to now we have a lot of finished. Yes. Thank you. Yeah, this is a good question.
Thank you very much.
Okay, we have actually time for more questions. So are there any more questions for Professor Zhu? Okay, I just have a short one. You mentioned before this weakly pseudo-convex domain. Mm-hmm. Is this any presence of these things in the results that you present?
Sure. As I mentioned, for Grout proved the Levy problem on complex manifold. Okay. So he got that if the complex manifold is strongly pseudo-convex, this means we have a strongly smooth Fourier subharmonic function, which is exhaustion. Then this is Stein. So this means this manifold can be properly embedded into some complex Euclidean space. He also gave some example. If this is not strongly, just weakly pseudo-convex, then this manifold may be not holomorphically convex.
Yeah.
Yeah, so there are many examples which is weakly pseudo-convex, but not strongly pseudo-convex.
Yeah. Okay. Of course. Yes.
Yeah,
Yeah, and then of course there is there is also such examples when there are no domain of holomorphy, etc., and so on.
yeah. Not holomorphically
Yeah.
convex. Yeah.
Okay. Okay. Thank you very much for this talk, and so let's thank the speaker again.
Yeah, thank you.
Good morning, Professor.
Yeah, good morning.
Can you hear?
Can I share the screen now?
Here, here. Okay. Will you share your screen?
Yes, yes, yes.
Okay. We see now.
You can see. All right. Good.
Yeah. How about your camera? We cannot see your face.
Just 1 second. I'm not sure how to do it together with this screen which I have. I'm not sure how I can do it. In any way, I'm doing it from a iPad, and then my camera is sort of on the on the side. It would be not very pretty anyway.
I see. Okay. Then maybe we will start in 10 minutes. Maybe first you will show your face. This is just to check if everything works. Okay. Now, in 10 minutes, maybe you will first show your face, and then explain, and then share the screen. If I think that should not be the problem.
Let me stop sharing the screen. Okay. Understand what's going on. What we can do, I can also log in into a computer, and then maybe I can show the screen, okay? Show my face. Can you see my screen now?
Yes, I can see.
Just 1 second. I log in through the computer. Right.
Now we can see you, but can you mute one of the devices here?
I know. Yes, that's what I'm doing. And also,
Can you hear us?
I can hear you, yes.
Need to switch off one of the devices, maybe from the iPad.
All right. All right. Can you hear me? Can you hear
Yes.
me? Can you hear me?
No,
Can you hear me?
it is still we have. Now,
I think now it's better, right?
yeah. Can you say once more something? Let's check.
Yeah.
Yes.
So everything is okay now, right?
Yes. Thank you. So the people are coming now. Maybe we'll start in 5 minutes. Okay?
And wait, yeah. So,
Okay, thank you.
sorry, but I don't see my slides anymore.
Yes, we can see your screen.
You can see my screen. Okay.
Yes.
Okay.
Раз, раз. Good day, dear colleagues. Our next speaker will be online. First of all, it is my great pleasure to once again welcome all of you to Kazakhstan and to the largest mathematical event in our region, the ISAC Congress. Thank you. Today, I have the honor of introducing our plenary speaker, Professor Ari Laptev. Professor Laptev has led an eventful life. He received his PhD in mathematics from Leningrad State University in 1978. As he once shared with me during our meeting in Turkey 2 years ago, during the totalitarian period of the Soviet Union, and he was even forced to work for several years, 5 years about, in a lodging camp and in the building as a worker. And thanks to the intervention of the British government and by the decision of the President Gorbachev in 1988, he was eventually permitted to leave the Soviet Union. And since return to mathematics, Professor Laptev has made numerous important articles, over 140 research papers in leading mathematical journal. He was president of European Mathematical Society, and he was director of Mittag-Leffler Institute of Stockholm. Currently, he holds the position of professor of pure mathematics in Imperial College, London. Please, Professor, the floor is yours.
Well, thank you very much for this introduction. It's almost correct, but some details are sort of missing. Anyway, so I'm very grateful that you invited me to give this talk, and it's a great pleasure. Unfortunately, I couldn't come to Kazakhstan, but it's just I'm sure the Congress goes very well, and I'm very grateful to I appreciate the organizers who've done a tremendous work for organizing this Congress. I mean, I know very well how difficult it is, and then you've done a very good job. Thank you. So let me start. So there's something which I'm going to discuss is the sort of spectral property of some functional different operators for mirror curves. And this is the plan of the talk. And that is sort of consists of 4 parts. And it's a kind of review for something which we've done regarding the program of these operators which we have, and that is just the results during the last decade, roughly speaking. The first part was done sort of about 10 years ago already, and this is the so-called discrete eigenvalues of Weil operators with increasing potential. Then about a couple of years ago, we obtained also these inequalities of Lipp-Tearing type for self-adjoint Weil operators with decaying potential. Then only about a couple of months ago, our paper on a self-adjoint Weil operator with decreasing potential was accepted in a journal, and then it's about location of the eigenvalues. So, and finally, I have a number of open questions, which we also can discuss a little bit in a self-adjoint case. So let's begin with the discrete eigenvalues of Weil operators with increasing potential. Let me first define what these operators are. So, so what is Weil operators? So what is Weil operators? It's, we introduce operator U, and that is in the following. We take a function psi, and we take x belonging to a real line, and then we have IB. I here is a square root of -1, right? So it's and B is a positive. Then another Weil operator is just multiplication by this exponential function. Now, we have this kind of commutation relationship, which is sort of appreciated in the theoretical physics. Of course, basically, it's related to the how differentiation and then the multiplication operator commute. And then, of course, here we don't have so-called analog of differential operators, but it will come in a moment. Now, in order to, as I learned being a student, so it's not good to just look at the action of how the operator works on a function, but you also have to define a domain. And obviously here, psi has to be kind of analytic, right? And sort of it has to be, at least analytic continuation. And in the Fourier space, the domain of the operator U is the following. If you take Fourier transform, then it's just shift, and shift becomes multiplication by the exponential function here, and that has to belong to L2. And here we just our major space is L2 space, and then it's just a multiplication operator. We define those psi so that then it is a multiplication by the exponential function belongs to L2. Therefore, if, for example, x goes to plus infinity, then psi has to go to 0 more rapidly than exponential function. There is another description of the domains of these operators. It's a more straight. So, for example, domain of U, this shift by IB, is the following. It's just it's those analytic continuation. The function psi can have analytic continuation on the strip, and then the this limit when we approach the upper line x plus IB, then it has to be an L2. So then, of course, naturally we can define U to the power -1 and V to the power -1, and that is just give through these expressions. Now, so the main object which we just covered today in the first part of my talk, that is the how the spectral properties of this operator. So what is the U plus U minus 1? If you take Fourier transform, then it would be just, this one would be multiplication by the exponential function, and then this is multiplication with the exponential function with a minus argument, and that is that would be just 2 cosinus xi, and then multiplication v plus v minus to the power v to the power -1 is just multiplication by this function cosinus, and that is usually when we speak about symbols of differential operators, that could be regarded as a symbol of the operator H. Now, that sort of operators appear, in different forms. Variety of these operators, while operators appear in the different sort of forms, and then and these kind of operators are very useful for problems in theoretical physics. And then, for example, these operators, while operators U and V, appear in the study of local mirror symmetries as a quantization of algebraic curves with a mirror to toric Calabi-Yau thresholds. And the spectral properties of these apparatus were, I mean, it's just enormous amount of papers, and that was considered by many others, many people. Now, so one of the things which I became involved, it was a sort of when I listened to a talk of Leon Takhtajan, who presented his paper together with Ludwig Fadeev, and then they were studying this apparatus, and then they studied spectral properties of this apparatus. Of course, this apparatus is and if you look at the symbol of apparatus, if you don't have V here, then this apparatus, what is it? It's a in a Fourier space and multiplication by 2 cosinus hyperbolicus. Now, and that immediately implies that it's the spectrum of this apparatus is absolutely continuous and covers the half line from 2 to plus infinity twice. But of course, if you add an increasing potential here, then it sort of covers only once. So that was it. And then, well, I just have these remarks about so what people did here, and then people studied the spectral properties of this apparatus with the continuous spectrum. This apparatus has just pure continuous spectrum. However, here we have sort of differential part, and then we have increasing potential. And one could expect that the spectrum of this apparatus is discrete. So, and then there is no absolutely continuous part. And indeed, so what we've done, we found the actually wireless asymptotics of this apparatus. So a wireless asymptotics could be obtained for different objects, and then one of them, the classical object, is the Rees means. And that is the following. This is one, I mean, assume that the spectrum is discrete, so lambda j, the eigenvalues of the operator h they converge to infinity. When j goes to infinity, we enumerate them in an increasing order. And then, of course, what we have is we study lambda minus lambda j plus. What is plus means that we only study those. Here we make summation only over those j's that so that lambda j is less than lambda. If lambda j is greater than lambda, then this plus says that this quantity is 0. And then when lambda converges to infinity, we have more and more terms in this sum, and then there is an increasing. This sum is increasing, and that is the following. This is the exact formula, and this is an arrow term. I mean, using standard Tauberian theorems, we can also sort of obtain the not only the spectral asymptotics for the Rees means, but also we can obtain the asymptotics for the number of eigenvalues below lambda. This is a standard Tauberian theorem, which is sort of, I'm not going to mention, but one can obtain the asymptotic behavior of n of lambda. It's a classical object also, you know, it's sort of like people, since time of current, people studied this object in different, for different operators, and then we have the following formula. And then, of course, roughly speaking, what we have is that if we take this formula and differentiate formally with respect to lambda, then the main term here is that when this lambda disappears, and then we have logarithmic behavior, and it's exactly logarithmic behavior which appears here. So, I mean, and then everything else goes to a remainder term. All right, so this is the result. And then let me mention a little bit about how we prove it. So there is a very, from my point of view, elegant proof using the so-called covariant state transform, which is very, very good in many ways. And I think that in many cases, it's a very short and very explicit and a very pretty way of obtaining different type of wireless asymptotic formula. So what does it do? So what we take is that we take a function psi from L to R, and we multiply it by this one. So it's almost a Fourier transform because we have this exponential, and this is our psi. And then also, but it's also localized Fourier transform around point X, right? So here G is just a Gaussian, but it doesn't have to be Gaussian. It could be any even functions, and then we also normalize it. And then what happened is that we have a function of two variables now, and then it's just so one can say, what is the point? The point is the following: if you just have a differential apparatus with a constant coefficients, then of course operating with this, what do we do? I mean, if we take Fourier transform, then the operator becomes multiplication operator, and if you have multiplication operator, we know how to construct inverse, how to construct a function of this operator, and then so it's very easy. But if you have a differential operator with a variable coefficient, that is not easy. I mean, that sort of becomes a problem. So the idea of the covariant state transform is to solve for such operators. And of course, we can't get identities here because, of course, it's not quite sort of, I mean, you see, so it's sort of like, it's not really, we have an operator with a double variables in R2 instead of R, we have R2. But however, it helps very much. And then it's sort of what we do here is that usually covariant state transform allows us to see how operator looks like. And it is a multiplication operator. And then the first term of, I mean, there are many terms. And then the first term is precisely the multiplication by the symbol of the operator, the main symbol of the operator. And then we have arrows. And arrows we can sort of treat in a different way and obtain sometimes what we want. And what is this phi capital is that if we take phi star phi, then we first go to L2 R2, but then we go back to R2, but then we go back to L2 R. And then sort of we see immediately just by integrating with respect to psi here, because just it's Fourier transform here, and that is just would be delta function, and then we get a gain function. So it's identity operator. And of course, one can expect that it would be identity operator if we swapped phi star and phi, but then it's just a projection. And it's also, actually, you can easily see that it's an orthogonal projection. One can write a kernel of this orthogonal projection, but it's not particularly interesting. So let me just explain how it sort of works an example of harmonic oscillator. So if the symbol of harmonic oscillator is basically psi square plus x square, right? So if we take this psi square and then first to go to the covariant state transform, and then multiply by psi square, and then we take inverse or adjoint of covariant state transform. Then we have this expression, and then just integrating by parts, we immediately obtain this one. And what it is, it's, you see, it's basically, it's what we have, it's a quadratic form of the first derivative, right? Which sort of after integrating by parts gives you the second derivative minus second derivative of function psi. But then there is an arrow, and this is just a constant. It's just a constant, and then this is a L2 norm of the function. So similarly, we do with the multiplication by z square, and we get this expression. And again, here we have x squared psi square, and which is just quadratic form of the multiplication operator by x squared. And here what we have L2 norm, and then here just a constant. So summarizing, we're taking these two, put them together, and then what we see is that the derivative, the quadratic form of the harmonic oscillator, which you have here, is actually a multiplication operator, but there is an arrow, and this arrow is exactly this one. Is just a shift in L2 space, as shift by precisely all these things. So it's not so coherent state transform doesn't sort of allow you to transform the harmonic oscillator to the multiplication operator, but almost, right? So it's almost true. So what we have here, we have just multiplication, and then here we have some arrow. Now, let's return to these operator, while operators, which we consider here. And this is a remarkable identity which we have. Now, what normally happens is that if you have general differential operator with variable coefficients, and then you take the coherent state transform of this operator, and then it sort of becomes multiplication operator by the main symbol, but a principal symbol of the operator. But then it would be almost always you can get an infinite number of arrows, and it's kind of very complicated expression. What is remarkable here is that we have identity. Like with a harmonic oscillator, we have this identity. So basically what we have is if we take quadratic form of this operator H, then it's actually after coherent state transform, it becomes the following expression. So where are the arrows? The arrows here is D1 and D2. This is in a multiplication form. One can say that it's just, but in general, that what we have here, we have cosinus of the symbol of the differential part, so-called, and then the multiplication part, So, and then these expressions for D1 and D2 could be obtained explicitly. So that's how, and this is a L2 norm of U V plus V to the power minus 1 applied to the Gaussian, in our case. So, they are exactly, we can compute it as exact expression. So I think it's an amazing form. And I wonder, it's not very often, as I say, that it's normally what one have when one apply coherent state transform to a differential operator. You can't really see what the errors are. Here, they are all explicit. And that's what is nice about this technique. So then in order to obtain the wild formula, then one can use a sort of two sides estimates. So what do we do? What we consider the discrete spectrum of the operator H and then corresponding eigenfunctions, which are orthonormal system of eigenfunctions in the L2. Now, so of course, clearly, we can, instead of lambda j, we can write this expression. We apply H to psi j, then we get lambda j, and then because psi j of norm 1, we get just 1. And then to this one, we apply the, it's a quadratic form, and then from the previous slide, the result from the previous slide is just, we obtain this expression, right? We also can even multiply lambda by double integral of this one because it's equal to 1, right? So that's what we have. And then we have to take plus, positive part of the whole thing, right? Now, the first identity is exactly what we had in the previous slide. I just put it again. But then the first trick here is the following. So if you have integral, double integral of some function, and we have positive part of it, then we can put plus inside, and we get an inequality. And that is, we just get rid of the possible sort of places where functions inside the integral have positive and negative parts, so we take only positive part. So, and that is the first trick. So we have this expression, but then what we have is that, I mean, what do you do with this sum, infinite sum, right? It's just not that simple. So, because we don't know psi j, and then we don't know the coordinate state transforms and so on. But let's look at what it is. Let's interpret it. And this is a second pretty point in this argument. What we can see here is that, so what is this sum? This is, by the way, just Fourier. I mean, this is a coordinate state transform, and that is an integral or a scalar product of this function, Gaussian times exponential function, with the psi j. And psi j is the full system of eigenfunction. And then it's what we write here. We write the Fourier coefficients of this function e, x, psi, y, in the basis of psi j. Right? I mean, they're Fourier coefficients. And then what is the Fourier? I mean, we take sum of the squares of Fourier coefficients. It's Pythagoras theorem. We get a norm of this function, and then when we compute the norm, of course, it's equal to 1 because g is a Gaussian and it's normalized function. So, and therefore, this is the first inequality which we have, and this is an estimate from above, and this is of course, we have D1 and D2, but it's not a very great deal because we can think about them as an arrow. And if lambda goes to infinity, then the main term of this expression is precisely this one, and then everything else goes to an arrow. Now, using even simpler argument by using Jensen inequality, one can obtain the inequality from below, and it's the same thing, but it's slightly different. So here we have to multiply, but here we have to divide by d1 and d2. And again, I mean, analyzing this integral, we obtained it when lambda goes to plus infinity. We had exactly the same expression in the main term, and then some arrow. And this is basically the end of the proof. So one just a curious remark about it. So of course, I mean the symbol of this operator is greater or equal than 4, and then but I mean for cosinus psi and cosinus cosinus of x, one can write the sort of Taylor decomposition, right, like this. So we start with 4, and then we start with the second term when n is equal to 1. And then we have the remainder term, right? So you see, and this is this part corresponds to a positive differential operators. I mean, for each n, it's a differential operator of order 2n. But I mean, from here we immediately obtain that we have 4 plus symbol of harmonic oscillator, and for harmonic oscillator, we know what the eigen value is. So that means that basically we can say that lambda 1 is greater than 4 plus the first eigenvalue of the harmonic oscillator. And 4 in this case is just a shift of the of harmonic oscillator. And then it's just by variational principle, then we get this inequality because we just forget about the very huge positive part of this operator. But we still don't know what the first eigenvalue of this original operator is, and it's just I think it's a curious question. Hopefully, eventually, I sometimes give it to my students, but so far it wasn't successful. Right. So this is the first part. Now, I would like to say something about the inequalities for self-adjoint Weil operators with decaying potential. Let me begin with some classical stuff. So let's consider some trace formula for Schrödinger operators, which are very well known and very well established, and then show to be very, very useful. Now let's consider a Schrödinger operator on the real line, and then and if potential V is, say, compactly supported, nice, smooth function, then when x, we can have some initial conditions when x goes to plus infinity as an exponential function. And then when we go to the left, again, potential is compactly supported, then we have identity with a linear combination of two exponential functions. And then, of course, if V is non-trivial and is positive, say, then we obtain some negative eigenvalues, finite or infinite number of them below zero, because we subtract from the positive operator, which is the second derivative minus second derivative, we drag eigenvalues through 0.0 by subtracting a positive potential, and that's how these eigenvalues appear, negative eigenvalues appear. Then using Wronskian identity on the right, considering this on the right and on the left, then we immediately obtain this so-called magic identity. It's according to Barry Simon, who called it magic identity for the scattering data. This is A and B are scattering data. So in 1971, Fadeev and Zakharov, in the first volume of the first issue of the Journal of Function Analysis and Application, which was established by Gelfand, they studied the Korteweg-de Vries equation. They found infinite number of integral of motions, and then each of them connect. And then a sort of trace formula which sort of connect the spectral data of the operator, namely the eigenvalues and then the scattering data with the potential. And then the first two formula look like this, and that is the second formula, so-called. The first formula is a kind of a curiosity, which is very beautiful, but not particular, so not to be very particularly interesting. But the second one was extremely interesting, and then it's a sort of contributed in the wonderful paper of Lieb and Thiering when they studied the stability of matter. And this kind of formula became very, very useful, an estimate from above of the negative spectrum of eigenvalue Schrödinger operator. Since from this identity we see that modulo A square is greater or equal than 1, then this integral is positive, right? And then we can take it away, and then we have an equality from below, for the sum of the eigenvalues to the power 1/2. And then here, we can also dismiss it, but because it's positive, then we get estimate from above for the 3/2. Later, this inequality was generalized to a multidimensional case, and then that sort of was very, very useful in as I mentioned, in problems of stability of matter. Lieb and Thiering in their paper, they also studied this sum of the eigenvalues. By the way, sum of mu j to the power 1. This is exactly the energy of the system, of atomic system. And then and that is that's the most interesting case, of course. But they studied a variety of these kind of inequalities for different powers of I mean, instead of 3/2, they studied different powers. And then they noticed that the 1/2 is the limiting case, and then they even claim that they obtain inequality, I mean, from above with the power 1/2. But it turns out that it wasn't correct, and then the argument wasn't correct, and then later, then they actually proved this inequality. So then in the paper of Hundermach, Lieb, and Thomas, they proved this inequality for the Riesz means, or for the modulus of the eigenvalue to the power 1/2 with a sharp constant, and this is what it is. They proved this inequality. So that is a remarkable inequality. And then the first proof of a sum constant, which is not sharp, 1/2 here is sharp, but the sum constant was proved by Timo Wild, my former PhD student, and then his constant was above, greater, a little bit greater than 1. But then there was also another version of the proof of this inequality, which we obtained in the paper, a joint paper with Hundermach and Wild. And it's slightly different method, but basically it's very similar. What is remarkable here that the power 1/2 it stands out in an amazing way, and we have two-side estimate for, I mean, arbitrary V. So what is interesting about all this inequality? They are uniform with respect to V. Whenever you have V, which is integrable, then you have this inequality, right? You know, that's what it is. I mean, we always assume that V is not negative. Now, so we would like now to study our while operators. We say we take W B 0 and W 0B is exactly this is W 0B is exactly applied to psi. It's exactly psi x plus IB and plus psi x minus IB. So I mean, as we already saw it, there is a cosinus, hyperbolicus, -2, and then of course it's greater or equal than this expression, and therefore, I mean, what we do is that if by variational principle, if we just dismiss all these positive parts of the operator, then in principle we can obtain what we want for the while operators with W0B minus potential, and then immediately we obtain this inequality, and that follows from this one, you know, due exactly to the fact that we have the simple inequality on the differential part of the operator, and then but it's not satisfactory because we can actually do better. Because, I mean, again, we just, when we consider this inequality, we just take away huge positive operator, which corresponds to the Taylor decomposition of the cosinus hyperbolicus with greater terms, you know. Now, so, and then now what we have is the following. So let's consider V negative, and then we have this WV, we denote by WV psi, this operator, which is the while operator with V, which is decaying function, and that is the action. So what is good here, we can parameterize lambdas, eigenvalues of these operators, negative eigenvalues below 0.2. Of course, the continuous spectrum of W0B is from 2 to plus infinity. It's absolutely continuous part. And then when subtract V, then it drags from, say, continuous spectrum some eigenvalues, which we consider below 2. So, and then we parameterize them in the following way through omega j, and omega j, what is here, if omega j belongs to 0 to pi, And what happens? If it's equal to pi, which we don't allow, then cosinus omega will be -1, and then we have here minus, and we have 2. So we actually exactly at the point where the end point of the continuous spectrum. So we don't allow point pi. But 0 we do allow it, and then when omega j is equal to 0, then cosinus is equal to +1, and then we have exactly -1. In order to, I mean, of course, the eigenvalues don't know anything about omega much, and then they could be even below point -2. So in order to obtain them through this parameterization, in order to obtain equation for lambda which belong to below -2, we have to go to complex space, and then if we consider omega j such that they belong to the half line, complex half line, then basically the cosinus becomes cosinus hyperbolical, and then that parameterized eigenvalues below -2. So in fact, in our next statement, second statement, we assume that V belongs to L1, and then so we also have a big assumption that the potential V is not that great, so that it's small enough so that when we subtract it from the main part, from the differential part, then the operator is greater or equal than -2. So we only can consider a small perturbation, relatively small perturbation V, so that the whole operator is greater or equal than -2. Now, and then we have this identity. And this identity, it's a bit, looks a bit strange. I mean, the right-hand side part is just what appears in these Liptirian inequalities, which we mentioned before, for the this means of the module of eigenvalues to the power 1/2. And here, instead of this means, we have this sum. And this is much more precise formula, and you see that it's a sharp inequality. So the main ingredient of the proof is the construction of the so-called Biermann-Schwinger operator. And then what we do here is that we consider for that we need to consider the resolvent of the operator, Anpetov operator, right? So how to define this? How to find this resolvent? It's very simple, of course, because if we take a Fourier transform in a Fourier transform space, W0 becomes 2 cosinus hyperbolicus, and then we subtract our lambda, which we parameterize lambda is equal to this -2 cosinus omega, and then we take inverse Fourier. And then when we take inverse Fourier transform, which is just a little bit of a complex analysis, we do it through Residue formula, then what we obtain the resolvent, and resolvent is equal to precisely the expression. So, and then from this expression, we see why we have already some sort of, we can already see something related to the fact that we only can consider the eigenvalues or operator which is greater or equal than -2. So when we have lambda belonging to -2, and then we have omega j belongs to 0 to pi, then we are all right. So then when we look here, we see, I mean, then the function g is basically it's an even function, and also it's decays, right? Because and also it's a sinus hyperbolicus. I mean, it's a positive function. It's not negative function. Of course, it's 0 when x minus y is equal to 0. Then we have 0, but otherwise it's a non-negative function. But when we have omega belonging to this half line, and namely that when lambda j less or equal than -2, then sinus hyperbolicus become a usual sinus, and it's oscillating function. And therefore, we can't do much about it. At the moment, at least, we can't do much about it. So just let me finish speaking about the proof, just mentioning the following. First of all, when we compute this g lambda at 0.0, when x goes to 0, this resolvent, the main part of the resolvent, then using L'Hopital rule, we have exactly this expression, and this you see then this quotient sinus omega divided by omega just is involved in the final formula, in the final estimate of Lipp-Tearing type inequality. Now, then the Biermann-Schwinger operator, which we construct, is the following operator, become the following operator, and it's an integral operator. Instead of, I mean, what is the beauty of Biermann-Schwinger operator is that originally we had a differential operator, or kind of a generalization of differential operator. But then by manipulating a little bit and then reducing the problem, spectral problem, to the Biermann-Schwinger problem operator, then we reduce problem to the integral operator, an integral operator with this kernel. And the remarkable thing about the Biermann-Schwinger method is the following. Then if you fix lambda and let lambda is equal to lambda j, which is the eigenvalue of the original operator which we had, then we can consider mu j. I mean, usually this operator is compact, and then the spectrum converges to 0. So, and if denoted that's operators by mu j, the eigenvalues of this operator by mu j, then the mu j corresponding to the k operator k lambda j, right? It's exactly equal to 1. I can do it a little bit more careful in a couple of slides later when we consider the non-self-adjoint case, and then we shall understand it more. But just let me believe it. And this is a key point. And then there is a story behind, and it's I gave a talk once in and that is also a crucial point even for the Schrödinger operator when we consider this Riesmans with 1/2 Riesmans for the Schrödinger operator. And that was once I gave a talk in Lund, and then there was Lars Scherman that was in the audience, and then she looked at the proof and she said, well, not that many operators we can
sorry, Professor.
understand this method.
Professor,
Right?
sorry, you have 5 minutes left. 5
minutes.
Yes.
But I started quarter 15 minutes later.
15?
Yes, because when I started it was quarter.
We need time for questions.
Okay.
Thank you.
All right. Anyway. Okay, thank you. Okay, so let me just mention, since I have only not that much time, but then I was planning for 1 hour. But anyway, so now I understand that it was a mistake. Now, so let me just say a few words about the non-self-adjoint case. So what we have in a non-self-adjoint case, we consider again while operators. I think there is a little mistake here. It's can write 0 here. And that is a, and it's exactly the same expression, but V here is a complex valued function. And then here it's naturally, I mean, as you remember, then what happened before, then if you have a real V, then so what we can consider omega from 0 to pi, and then we had also a complex plane here, like this, right? Here, what we have is that in order to cover the eigenvalues could appear in the whole complex plane, and not only on the real line minus infinity 2 plus 2. Here we have sort of the following situation. We have to consider the strip like this, and this is our omegas, and that is a conformal mapping that sort of minus 2 cosinus omega. We move to conformal mapping to lambda, and lambda now belongs to C minus 2 infinity. So we have we can cover the whole eigenvalues which belong to the complex plane, apart from the part where the operator has a continuous spectrum. And that is an inequality which we obtained here, and that is an inequality sharp. And just what is a curious thing here, let me just skip, since I don't have time, let me skip the proof. You can, I send my files to Durwood Hunt, so you can always sort of look at them. And then what is interesting here is that one can compute the eigenfunction, at least for the very particular case. So if our potential is delta function, then we have rank 1 perturbation, and then here we have eigenvalue equation, and then here C is a complex parameter, and we can consider C as a sort of r to the power e to the power I theta. And then theta we can run along the circle. Basically, this is a description of the circle. And then what happened with the spectrum of this operator. And then the spectrum eigenvalues of this operator can be computed explicitly. So what we have is that the eigenfunction, I mean, we can take Fourier transform. I mean, the W0b would be cosinus hyperbolicus, and then we and this is just a delta function, just a constant, and then we just solve this equation immediately, and then finally take inverse Fourier transform, and that's how we obtain the eigenfunction, basically. And then if we let x going to 0, we can obtain immediately the following identity. So this is an expression we describe you through this parametrization, which we have that omega or lambda is equal to minus 2 cosinus omega. That's sort of related to the eigenvalues. And this is a relationship with the constant C in the potential, right? And then there are pretty graphs which you can consider, and then sort of describing what we have here. This is our solutions with respect to omega. If omega runs from 0 to 2 pi, if theta runs from 0 to 2 pi, we have these omegas here, and this is a graph. And then when we compute the eigenvalues, and that would be this part only. Now, we have several circles here, but it's related to the fact that, I mean, eigenvalues would belong to L2, and that is, I mean, the eigenfunctions to corresponding eigenvalues belong to L2 only if we consider this part. And the other part, that is sort of when we considered omega, what we considered only this part, right? This part of the complex plane, part pi. But if we consider this part and further on, then we have resonances. And these resonances appear, in this further circles. And what is resonance is just solutions of the equations. But when your eigenfunctions, corresponding eigenfunctions, are not from L2, they don't represent any eigenvalues. So this is another picture, and it's for different R. So we have different R's, and then what we have here, and then sort of this. This is the case. Now, I would like to borrow another 3 minutes to sort of speak up a little bit, return a little bit to the sort of open, to the self-adjoint case and open questions. So we can consider, again, while operator, and it's a free while operator, and then it could be useful to consider these two operators, which is just would be identified with the differential operators or some kind of an analog of differential operators of first order. And then we have this, of course, this identity, and that solutions of this one, when we apply W0, this operator, then it just would be exactly this one, and it's we have this sort of identity. Here we would like, because we deal with the continuous spectrum, they are not eigenfunctions, of course. They are generalized eigenfunctions corresponding to the continuous spectrum of the operator W0. It's easy, it's good to parameterize this spectral parameter by lambda cosinus hyperbolicus rather than usual cosinus. Now, there is a very well-known fact, and it's sort of Kossarati determinant, and this is a it's basically an analog of Wronskian. And then what we can do is that, there are sort of, it's again, here it's a proof that likewise in the usual Wronskian, then the Kossarati determinant also is a constant. And then in particular, when we consider now while operators with a decaying potential, and V is a real valued function, and then what we can, by what we already had, we could see for the Schrödinger operators when we considered Buslaev, Zakharov and Fadeev trace formula, then we can do this analog. Then function psi is equal to Yost function when if potential is compact and supported, then we have a sort of a free equation for free part of the only differential part existing. So we can consider on the right hand side just this Yost function exponential, and on the left hand we have scattering data. And then what we have is that finally checking all these properties of Kossarati determinant, that it's a constant, precisely the same way as we have it for the second order differential operator. And then we have this magic identity. And then related to what I said now, we can say some open problems. Usually we know that for the Schrödinger operators and a solution of Schrödinger eigenfunctions or eigenvalues of the Schrödinger operators, they are simple, and then the smallest eigenvalue doesn't change sign. Is it true for the Weil operators or not? Then what would be the Gelfand-Levitin type of equation? What would be is there a chance to solve the inverse problem for this operator using spectral data to obtain the potential U? And what would be the most interesting case would be the generalized trace formula. And in particular, what would be the Korteweg-de Vries type equations or Lax pair and all these sort of things. So So this is sort of open questions, and then what we had is that we sort of actually working on this trace formula, and it looks promising. We haven't finished yet, and we work together with Luca Schirman and Leon Tartajan right now, and it looks very promising. You got through a very important sort of thing, and now try to solve some type of Volterra type of equations. But anyway, so we expect that trace formula might be holding, and then how they look like, we have no idea yet. So that is that basically all I wanted to say. Thank you.
Thank you, dear professor, for your wonderful report. Dear colleagues, who has questions, comments? Please.
Okay, thank you very much for your very nice talk. I have a question related with the first part of your presentation, right? When you present the biasymptotics for your operator, then you have your lambda, log square lambda, first term, and later your lambda log lambda, second term. My question is if whether or not it's interesting for you to improve the second term from the big O lambda, from the big O notation of lambda to the small o, right? Or if you are interested also in getting the third term for these spectral asymptotics.
Yeah, so yeah, it would be interesting, but I don't know how to do it. I think it might be difficult. I mean, definitely coherent state transformation wouldn't do it because you have an arrow and it's sort of they influence the second tone. That's true, but I mean, how else can you do it? I mean, maybe you can do it by using this sort of partition of unity, roughly speaking, like what Kuren did in his book, you know. And this is, it's not that, I mean, once I discussed it with Grigory Rosenblum, and then he actually asked me the following question. I mean, and then, are there any method apart from this sort of variational method with split and Dirichlet-Neumann bracketing, sort of robust method to obtain the wild asymptotics? And then, indeed, not many. I think coherent state transformation is one of them. Now, then the second terms usually are done through the constructing of, say, wave group, like what you've done. I mean, it's sort of in general, Dustermatt, Guillemin studied it, and then sort of some other people. I mean, in the multidimensional case, and then in general, it's not an easy problem because there are not that many methods of obtaining second term in a smooth way. And here, of course, we have a complication because basically we deal with the differential apparatus of infinite degree order, right? Because cosinus hyperbolic of psi is if you have infinitely many terms, I don't know, all positive, but still infinitely many terms. So, I mean, I don't know. It would be interesting, definitely, but how to do it, I have no idea.
Thank you. More questions? No. Thank you, Professor, again, and we wish you all the best. Thank you.
Thank you very much. Thank you.
We will go to dinner. Yes.